Okay, welcome to this last day of RootedCON. We begin here with Arán Lora and Victor Portal. They both work in Deloitte as consultants, and they are going to talk to us about VoLTE and its demystification. Thank you very much. First of all, thanks to the organizers for giving us this opportunity, and next to all of you for getting up early to come here on a Saturday morning. We know how Fridays can get complicated, so this is the structure of our talk. We will do a short introduction about what VoLTE is and how it has evolved until reaching this technology. Then we will talk about the architecture of VoLTE and VO Wi-Fi. Then we will explain authentication in this technology, and then we will talk about some approaches that we have found to be able to review this sort of environment. And finally, we will show a taxonomy of vulnerabilities, the typical vulnerabilities, things that we should look out for, and different passive and active attacks, the outlook of 5G, and finally some mitigation to solve the vulnerabilities that we have identified in this environment. So this is quite a general scheme of how mobile networks have evolved until we've got to LTE, where we've started introducing voice. So far, most of calls were being made through GSM, a technology that started at the beginning of the 90s, the second generation 2G. It's a technology that's based on circuit, not packets, so it is not IP, but the next technologies since have evolved towards IP technology. So everything afterwards is IP. After GSM, we had 2 plus 5G, which is what we call GPRS. Then there was a further development and improvement that's called ES, and the core is actually very similar, but it implements the transfer rate and it gives it more speed. And then the third generation came along, 3G or VTES, and here we get a greater speed, and finally we reach LTE. So in LTE, so far 3G and the others were data-based, and until LTG there was no thought of reintroducing voice or improving voice technology that was there and that we're still using. So this is a network which is very busy, and one of the reasons why we have decided to use to do voice over LTE from the user viewpoint, because the quality of the phone call is much better. The bandwidth is very optimized, so you're going to have a greater quality than using GSM or one of the earlier technologies, but through the data channel. So in LTE, there is a division in between two channels, one for voice and one for data, which is the one we use for WhatsApp in our mobile device, etc. So I just want to mention that each technology has its own core. GSM has its own core, and G3 as well. And within LTE, there's a new core, which is called IP Multimedia Subsystem. And the multimedia name is because it's always available for, or it's been designed for video service, everything over LTE. The access, a mobile network is divided in two networks. The access network, where you have your own frequency range, 3G, 2.53 or LTE. And then we have the core, which, as I've mentioned, is different in each technology, and And we will talk in the next slides about this core, which are the components of that core. So the deployments of LTE voice started in Europe in 2015, and for instance, Movistar deployed it last year. And so there are more and more users that are making calls through this technology. For the user, this is quite transparent. You just need an SIM card which is compatible with LTE and a device that's also compatible, which is the case for most of them. So right now there are millions of users that are performing phone calls with voice over LTE. We wanted to have some slides about how phone calls were GSM phone calls were made so far, for you to see how it has evolved. So, simplifying it a bit, I'm going to explain the communication flow and how the radio channel is established between the mobile device and the aerial, the tower that gives us the cell tower. So, this is how it works. The tower advertises its presence with its broadcast message, but it also mentions the configuration of its network, and these messages get to the device, and the device identifies itself and sends this type of message, an update request, and it sends some identification data. The IMSE is the better known one, which is like our user when you authenticate yourself. So it's the user that identifies us as a subscriber within a mobile network. Because IMSE is considered a personal data, then if the network is appropriate, it uses the TMSE, which allows the network to identify you, but if somebody accesses that network, it's encrypted, so they cannot identify you personally. So once the phone identifies itself in the network, there are a number of exchanges of messages, and depending on how the network is implemented, well, it will vary. Sometimes if it's a local mobile and you are connecting another network, it won't recognize you, and it will ask you for an identity. It would make an identity request, and you might have to send your email address, which is a single identification number. And sometimes it asks you to authenticate yourself if you haven't joined the network in a long time, if you've changed geographical area, etc. And after this exchange of messages, you start negotiating deciphering or encryption. And in this case, the encryption has been broken, this algorithm, because there are tools that allow to break this encryption and listen to your communication. So once you negotiate the encryption algorithm, the channel is established and you can begin to talk. Okay? So what we're talking about is an IP network, and once here you request the service, you send the configuration data, where am I making the phone call to, the codecs that I need to negotiate my phone call with, and then the network will send messages regarding the status of the phone call to notify how things, the attempt to find the person we want to reach, etc. So once that person is found, a connect is sent to the user, and the user can start talking. In LTE, the establishing of this radio channel with the cell is very similar. It's quite similar to GSM. There's only a difference in protocol. but the way in which you identify yourself in the network is pretty similar. So the network does the broadcasting, the device identifies itself with its IMSE or its email, and then the encryption algorithm is negotiated, and then you start exchanging data. So the robustness regarding encryption in LTE is quite good. We are not aware of any practical attack, so this channel is considered a lot safer than GSM. So after this introduction and providing some context about the mobile network technologies, particularly at the radio level, we're going to talk a bit about the architecture that we've mentioned earlier on, about voice over LTE and the different components. So here there's a reference to the technology that I was mentioning at the beginning, which is voice Wi-Fi. It's not connected with voice over LTE, but it shares code. The VPS is the same. As you can see, the protocols used here, both in Wi-Fi voice and LTE, the protocols that have become a standard in IP voice. We are talking about SIP for the control level and RTP for the data level. And just to mention that this Wi-Fi technology came up to provide an additional service to clients, or because there are cases where you can not have a LTE coverage or GSM, but you maybe have an access point and you want to make a phone call through that access point or in a transparent way. And we will see that the configuration here, the IPSEC, where the traffic is protected by this tunnel, and it has a different configuration, and we will explain that later. But to mention the two more important things within this core, first of all, the first thing we find if we look at the traffic in our device and see, if we sniff the traffic, the first component that we find is the proxy. The role of this service is just redirecting the packets inwards and connect the IPSEC with you. And once you go through this device is the second one, which is the interrogating. And the role of this device is to allocate an SIM service. And these interrogators exist because we're talking about something very complex. There are millions of users, so depending on the congestion, the interrogating allocates you to a different device and other parameters such as local geographical location, etc. So this IP server that controls the session and tries to get you in touch with the person you're making the phone call to, maybe that person is not using the voice LTE, and then you have to use this other component, the gateway, that gets you in touch with GSM. If we are making a phone call to a device that does not use this VoLTE technology. Finally, I want to mention something very important. This is one of the core of a mobile network, and it's where we find all of the information to do with the subscriber. This is where the IMSE is kept, and the services that are contracted, the rate that applies to you, and also an important part, which is the private keyword or key, which is stored in our card, but also in this part of the equipment. Okay, so I hope this is more or less clear. Now I'm going to talk about that IPSEC tunnel, or that I've mentioned earlier on. The safety of, or the security of the tunnel is based on this private key stored in the SIM card. The transport mode is IP within IPSEC. And the difference that I've mentioned earlier on between Wi-Fi voice and LTE is particularly relevant in the way in which this tunnel is established and the security features, the integrity algorithms or encryption algorithms that are used. In the case of Wi-Fi, I'm actually making phone calls using access points that can be exposed at an airport, a shopping mall, etc. So anybody could be listening, so it makes sense that the tunnel that you negotiate here has encryption. But in the case of voice LTE, the operators have not implemented the encryption. Why? Because this channel is considered secure. It's quite robust. So adding another level of encryption would worsen the quality, and that's why the operators have decided not to encrypt, but we do have this integrity protection to avoid the manipulation of the zip package. And because communication happens through internet, as we will explain later, there is the exchange of keys using the IKE protocol, IKE. And there is an application of the system, the IMS application. You can change there certain parameters of the tunnel. We can say do not use encryption, and if the network allows for it, then it will use it. You can change parameters connected with the SIP if you want to work with TCP or to try to disable the IPSEC tunnel, etc. I'm going to talk a bit now about the registry process in voice LTE. Once we have established the channel, we have registered at the radio level. We also have to register at the voice level to make use of the voice services, and the procedure is more or less simple. Regarding the SIP or the SIP protocol, it's a text-based protocol very similar to HTTP. If you use headers and verbs, imagine rather than register, we're talking about get, or rather than invite, we're talking about a post. But it's really very similar, header, etc. So the first communication flow is here. You see there's a SIM register with some identification data, which are as follows. Here you have the IMSI, who I am, then the IMEI, which is from what device am I connecting, and then the cell ID, from where am I making the connection. So this gets to the HECS, and it says, okay, the HSS says, okay, you have to authenticate, and it sends a challenge. And when the device receives the challenge, it sends it to the SIM card, and the card makes some operations, encrypts this challenge, so to speak, with the private key, and it sends it back in a second SIM register packet. And the HSS ciphers recovers the message and authenticates the mobile device in the network. And here the whole tunnel is negotiated, and then all ensuing communication will be protected by this integrity tunnel that I've mentioned earlier on. So Wi-Fi voice communication is done through internet. We do not negotiate a radio channel with the network, and here we have a device which is called the EDPG, which is this internet, and that goes to the port 500 UDP, and here is where it negotiates an IPSEC tunnel using the protocol that we mentioned earlier on. So the way in which you authenticate, it's the same. There's a challenge that's sent. You encrypt it with the SIM card, and after you establish an IPSEC tunnel between the device and and the internet device from the operator, and then there is a tunnel established to tunnel the information towards the core, because there are these two parts that are outside of this core. But this is just generally, because we will go in further detail about GTP. So before I give the floor to Arán, I just want to mention the flow for the beginning of the phone call. Once we've registered with the network using the SIM register, and with the process that I've just explained, there are a number of messages are sent. The person calling sends 3 messages, SIP invite, SIP prac, and SIP update, and the receiver sends these 4 messages back. So this is the flow you can see. You send the SIP invite, the other one returns a trying or a session progress, then you send the prac, they return OK, and then the communication is established, and from the last AC key you can start talking with the other party. It's important for the SIP messages that are sent from Alice to Bob. They have to go from one side to the other unless there's been a filtering of parameters, and you can imagine where the vulnerabilities are going to arise here. Okay, Arán, you have the floor. Good morning. How are you doing? After the explanation that Victor has given, we're going to go into how we can attack. Taking all the protocols involved, what we think it's more interesting when it comes to an attack is the protocol itself, because IPSEC and everything else is not so it's not so likely to be fruitful. Yeah. So the most important part of this is authentication. Victor has explained roughly how it works. But in the IPSEC tunnel authentication and in the SIP authentication, the SIM card is involved. It receives the challenge that Victor has mentioned. It receives an authentication token. It does a random to avoid the replay attacks, and this is sent to the SIP that does the algorithm that's here on the slide. I won't go into too much detail because that's not so interesting for us. And it gives back a password and a security key. These values, when we send them to the server, we are authenticated already. Just a minute. So these are different approaches because our goal here was to try to inject within this tunnel, to try to send SIM manipulated SIM packets. So you have two approaches, which is to replicate the whole authentication process as explained here, and from the device, in order to communicate with the SIM card, you need certain special features. There are operations that can only be performed with system applications, and then the other approach is to try to inject into the IPSEC tunnel previously created. So how are we going to implement this in the mobile device? Well, if we reverse the application that's being used, which in the Samsung Galaxy, I realized that this is based on Stronger One. Stronger One is a VPN client. It's free code, But the problem we find is that this type of authentication that connects with SIM, sends a token, you return that specific plugin is not implemented. So it's a proprietary development that's been done by Samsung. And that means that you have to waste time doing research and tracing, and to trace this communication in the mobile, we can use the filtrate, which is this device over here, which is just a debugger. And we place that between the mobile phone and the SIM card. And here we have the USB port. We connect that to the computer, and through the white trap we see the whole process as it's taken. And that allows us to implement. But as you know, when something has already been done, well, we don't need to reinvent the wheel, really. So if the mobile device already creates that tunnel, why not use it? And we inject ourselves in that tunnel, and we can send all the rubbish we want, or we sniff it and we can get all of the information we need to attack this protocol. So the Android implementation, this IPSEC channel, it's managed at the kernel level. If the Samsung is rooted, we can see all of the features, we can see all of the properties of the IPSEC tunnel. We've censored it because these are real data. We've had to attack in a real environment, but not so we have to censor as to not to compromise the operator information. These are the IPs in the tunnels and the keys, the verification, integrity verification keys. We also must keep in mind that although this is set up at the kernel level, the requester is a server in Samsung itself. Samsung itself has developed this service. But that's not the case in all devices. There are many devices that implement it directly in STM radio. So, and it's managed through software from the file itself, because if it happens at the chip level, we do not have the option of manipulating this tunnel and injecting inside. Something else we must remember is that for identity theft or for replacement, you generate the tunnel which manages this service. You set up an origin IP, a destination IP, and the port. And when we kill this process, the tunnel stays open because the kernel has managed it, and the process, that's the zip part. And if we are there, we can replace it and send all of the SIP protocol as though we were part of this process. My part is easier. Okay, so this is a bit of C code about the implementation that needs to be done. We can also use Python, and we have to be careful about the compilation in that case. And I have little else to add.
When we created this flipped client to impersonate the original client, we had to consider some headers that are sent that we have to include, and they have to have some certain values, because afterwards we have to parse some headers. This is very important because if we don't send it properly, the server won't respond properly, and we won't be able to continue with the test. Here we have some specifications about the headers, the most important headers that we have found that were necessary, with everything you need in each of them. Also, another thing that we have to say is that the Android itself, we can configure the expiration time of this tunnel because it has a limited time and it's constantly tunnel is continuously cutting, and we can modify that so it has a higher time and we are not being annoyed with it all the time. Okay, once we have the whole environment prepared, we can separate it in two big groups of vulnerabilities. We have passive attacks on one side, which are based on sniffing the whole communication that we receive, making calls, communicating with servers of client's core, and then the active attacks, that means using the client that I have just mentioned. Now we're going to explain each of them, an example of each of them, so don't worry too much about this. Passive attacks, it will sniff with Wireshark. If the connection is done as Victor indicated through LTE, this encryption going through LTE channel, this communication through LTE is not encrypted, it's just codified. Therefore, we sniff with Wireshark. Wireshark has an option to decode this traffic and it will show it clearly. Okay? It's not too complex. It's an option Wireshark that decrypts the traffic, and we see all the SIP requests. What we can find in this? We can identify the elements that are within the network, their IPs, software, the usual thing about fingerprinting. Here I have a little video to show the process, which is not too complicated. Here we are connected through SSH, SCH to the mobile phone with the command that we have run before. We have the information that I shown before. Okay. We see that the tunnel has been established, is created. We have some values assigned for coding, integrity and stuff. We are connected to an IP. With this command, we can see if the tunnel is open with the IMSI server. Here the IPs are all censored. This is relevant. Here we have seen that the communication has been created. Now we create a TCP dump in the interface RMNet1 and we assign it to a port. Therefore, afterwards, from our Kali, we run Wireshark, we select the ports of our computer, we run Wireshark, and that should be it. Actually, this part, once you understand all this, it's not, it's just running through 2 or 3 commands and that's it. You can see the ESP header, and when you codify it and when you decode that, you see all the SIP traffic. We can start inspecting which information is in the headers, which headers return the other end of the call. Apart from fingerprinting and stuff, what else can we find? As Victor mentioned, email is sent so that the IMEI, I-M-E-I, is sent so the operator can filter it. If it's not properly filtered, it can be received on the other end, both from the person who is calling or who's receiving the call. This information can be sent from one end to the other, and that's information that is quite sensitive. this is another thing which is more complicated. And when I was explaining SIP protocols, the identifier of the antenna to which it is connected, the mobile phone is connected, is sent. This is received by the operator, and with this identifier, we can enter this website. We can localize the antenna, the cell tower. This will be received by the other end, and without noticing, we could geolocalize them with a quite high precision. Then we talk about anonymous calls in the header from compared to the others. An anonymous ID is sent to identify it's an anonymous call, but apart from that, number phone is sent in other headers because the operator has to know the original telephone number that is performing the call. Same way, if these headers are not filtered by the IPSEC code, and it's going to be received by the other part, and even if the phone says that it's an unknown call, the packets will have the real name, real number, and that's not something that we want to do. We have to consider that this has to be done within the same operator. In a VoLTE call to a VoLTE call, because if it's moved, it switches to GSM, their coding is different, and these details may be lost. So this information could be lost. So it's more likely to find it within the same operator. Those were passive attacks. It just spend some time, know the important values, see what we receive from one side and the other side, and that should be it. Now we're going to attack with the client that I mentioned before. We created a small script to send information that we wanted to send, that it did a minimal thing just to make the test. And one of the important things that we found, as I mentioned, is the telephone number is sent in several headers. Also, if the operator doesn't look who has been registered or to which number it is that record is associated, and then it's not compared to the headers that are identifying the mobile phone, we could spoofing without much trouble. It's just spoofing and that's it. Changing it. Also, we can create additional headers apart from the ones that are specified in the protocol itself. We can create our own headers, and this will be sent from one end to the other. If it's not filtered properly, the other one will receive it. What happens here? The operator, this goes through a channel that is intended for voice in origin, but here we're introducing data, and the operator is charging you when the call is answered, not when you just send the first sending by. Doesn't make sense. So we do this from seeking by, and we start introducing information. We can create a channel, and through that channel we can send whatever we want, and this will go unnoticed for the operator. The operator won't notice. For instance, if we have two mobile phones, one is at home connected to our internet connection, to our Wi-Fi, we create a part of channel, and then we use another mobile phone, the one we use normally. We create a channel between those two devices. We can create a tunnel of internet connection, and that internet connection will be free of charge, or filter information that they won't sniff, they won't record that. Before we said the cell ID values, this is susceptible to be modified too. It's quite easy to, because in voice or Wi-Fi, they don't have a way to know the ID to which you are connected. If you are connected through a Wi-Fi connection, if you just you can deactivate the radio, and that's it. Here I have done a demo to see the script working. It's short. I have to say that the mobile operators are forced to keep a record of the calls performed and associate cell ID to which the device was connected when the call was made. That's why we send these SIP requests. If the person who did that call is involved in an investigation, that record must be there. And if we put something else, you cannot find where it was. Especially if we create a VPN tunnel, we connect a Wi-Fi through VPN, we change the ID. It's impossible to track. In that sense, we are a bit lost. The script has the most significant values in order to work. In this part, we have the mobile phone in screen share, the mobile which will receive the call. The script will make the call. This is running on the Samsung device that we have. We put the ports, entry and exit ports. We have the mobile phone that will perform the call, which ends in 4. This is not censored, the one who will receive the call. And there we have the value of the cell, the ID of the cell tower that we have spoofed. So we're saying we run it. We see the outbound traffic. The call is in progress. Here we see that the call has been received. We see the 4 there, as in the previous picture. Now we go to the screenshot that we received. We go to the header. We look for this value in the in-buy value, and here we see that the value that we introduce is configured. That's what the operator receives and sends. Here we see all the packets subsequent to the call that we explained in the previous slide. And then not much more to say. This same happens with IMEI. It's the code that identifies the device, the mobile phone itself. That this happens exactly the same. If we key the IMEI, we connect through VPN using voice over Wi-Fi. Police has a problem. Here it's the same values. This is exactly the same. You will see in this case we put the parameter M. They are quite simple examples, just that they are just proofs of concepts that this actually can occur. We receive the call. We receive the call equally. We go to Wireshark. We choose the invite, and we see that actually in the end everything is done through software. Everything can be modified. The methods that goes through radio chip, but otherwise the operator has to deal with it. There's no way to verify it. They could run some comparisons for previous values that had received through voice over LTE, but this is in the end those devices are separated one from the other. In principle they are not communicated among each other, so these verifications they are not conducted. Could we avoid it? Yes, but currently from what we have checked, it's not avoided. Well, playing more with our script, we started putting some stronger stuff, and the server can just block. You know, the usual thing, memory overflow, generating parse errors, creating injections. We can service derivation. We can create service derivation, and if we were the Niderman or any of these people who are illuminated people, we could get everything we wanted. And this is theory that will be explained by him, because he's better doing it. Here it's just to introduce the roaming, which is an interesting part in voice over LTE. Between roaming, there's a new component, which is the core infrastructure, which is the interconnection border. In the end, it's just like a proxy that connects a network to another, one operator's network to another operator's network. Imagine here that Alice is in a visiting network, maybe in France, and the proxy, the interconnection border, is going to get in touch with his home network, with her home network, to the one she's connected to, she's subscribed. So interesting headers in the implementation of roaming in voice over LTE. This is quite interesting. Network ID. Imagine in a scenario in which now in Europe we have this free roaming in all countries except for Andorra or Switzerland. Be careful if you go to Andorra and you leave roaming open, because roaming is charged there. So one thing that we could do is to manipulate that header to introduce the ID of a French operator with our free roaming operator with our operator, so that we didn't have to pay for calling from Switzerland or Andorra, with which we had a more expensive roaming contract. Well, actually, our operator's contract. Well, that's it. Also, that the IMS implements the messaging SMS service. This doesn't make much sense, because in EDT what we try is to achieve and improve on voice quality, and SMSs don't need too much space. We have the interesting features like from or entity that we could manipulate, and if the core doesn't filter it properly, we could spoof SMS and send SMS on behalf of another person. Another interesting thing is that in the end, both the GPRS or 3G or 4G are IP networks. In the end, our devices receive an IP address. From that IP address, we can reach other clients within the network. We could reach other elements of the core network. Normally, you have firewalls, and in any case, this scenario should happen. But when being able to inject ourselves in that tunnel, the visibility network can be expanded. Maybe that scenario has not been considered by the operator because of having a false sense of security through the tunnel IPSEC tunnel. But here there are some interesting scenarios. We can even discover services within the core network related to protocols that are used within an operator's core, which are quite obsolete. They don't implement any kind of encryption or authentication. But for those, in those cases, there have been reported attacks. For instance, the GTP port. If you look for a soda, you look on soda for this GTP, you will find many open ports, SCTP ports that could let you access to the SS7 network, which can conduct serious attack, like maybe the Metrobank's attack last year. They intercepted all the flow online. So in the end, there are messages for which you could access these networks that could provide you a battery of attacks that might be quite interesting. Also commenting Diameter, which is the successor of SS7 for 4G LTE technology, but here they haven't changed much. Even there are not much research about it. It's a good area for researching, but it is said that it inherits many problems of SSF. Just to conclude, provisions and forcings for 5G core and IMS is expected to be implemented in 5G. The only thing that will change is the radio regarding IPSEC RTP, it will be more or less the same. Maybe a code will be changed regarding RTP. They will improve call quality, but the functionality that we have explained may be applicable to voice over 5G technology. Also, we want to mention that the signal would be through HTTP2 and like SS7, which are some protocols are quite obsolete, and because the pile is quite complex, we're moving to HTTP based on APIs, a technology with which we're more comfortable with. And just to conclude, just mitigations. In the end, EMS, the main message is that you cannot trust to the in the other end of the only if you have an IPSEC tunnel with protection integrity. Those packages can be manipulated, and you have to conduct as an operator some additional variations within your core. You have also need to clean all your headers, not to expose information from one end to the other, like cell ID, the IMEI, all that identification information that says from where the user has connected, from which device. Also, network segmentation. We have to consider that this tunnel can open a window, a new window, but also for the demo that we just did, in which we manipulate the ID cell ID and the IMEI, that information should not be gathered from the voice over LTE. It's better to collect it from the radio part, from the radio record that we have seen it's collected to, the cell ID. That's obvious, and IMEI too. So that part is safe, because in the end all that communication is established through the radio chip from the baseband, and that's the traffic. The traffic, it's not easy, and there's no much communication for that. For voice over Wi-Fi, it's quite complex. So you have any questions or anything that you want to mention or discuss? I'm surprised because they are still awake. Good morning. From what I understood is that IPSEC tunnel is always done through your SIM with your ID, so you're identifying all the time. Another thing is that you can do the attack. Is that correct? Yes. When you mentioned that you can see the cell ID, is it your cell ID or destination's cell ID? The destinations, that what we said here, it's a return as a response in the conversation. That's the fun thing, to see the cell ID of the other end of the call, so you can geolocalize the other end of the call. That's awesome. At the level of IP connectivity with the core, have you achieved IP connectivity with something that is not your entry point? We could achieve things, yes. Have you achieved it? Have you done it? Well, yes, but we have discovered services to which you shouldn't be allowed to see. In the end, you just have to see an IP, which is the proxy, with the ISMS. The rest for you should be completely hidden for you. The fact of seeing an access port to SS7 or interacting with GPP, that can happen. Did you have with connectivity with SSH? I can give you more details, sorry. But you can find everything, that's it. It depends on the operator, on the filtering policies implemented by the operator. This is the human error factor. A firewall rule is not okay, or that the subject was not considered when establishing it. Any other question? Hello. Well, congratulations for your talk. Have you tested with a mobile phone that is not a Samsung S6? In the end, that's what we mentioned, that not all mobile phones implement voice over LTE at the level of the kernel. If we implement voice over LTE at the level of chip or baseband, you could sniff, because there are some tools to use it, but it's impossible to inject, or at least I don't know how to do it. And it's a way to do it would be listing the network interfaces of the mobile phone. You activate the voice over LTE, and you list the network interfaces, so you can see if the device uses it or not. At the moment, I had to deal with this case, and I had to on the mobile phones that are not S6, at least a year and a half ago, that interface doesn't appear. And I don't know if there's something to do to be able to sniff traffic, or is it impossible? It depends on the device. We could guarantee that with the Galaxy S6 family until S8, you could see those interfaces, which is voice, which is RMNnet 1, and the data, which is RMNnet 0, which is interesting for this speech. That could be useful. Well, we are merging this talk with the next one, so I will ask you, if you have any question, please talk to the speakers afterwards. We have to prepare the room for the next speech. So thank you very much for the presentation.